One way to think about your second year of physics or your year of AP Physics is to think about peeling back simplifying assumptions. And one of the huge assumptions that we've made for this first year and a half of physics is we've assumed all objects to be points. We have completely and utterly ignored their shapes. Now think what a boring world we would live in if all masses were just points. Right? We really don't want to live in that reality for too long. So what we're doing today is we're peeling back the simplifying assumption of looking at an object as simply a point, and we're going to start to consider its shape. In order to do so, you need to master something called finding the center of mass. Let's get started. On the screen you see a series of shapes. Okay, some are individual objects and some are collections of objects. The center of mass is simply that point in space at which we can consider all the mass to be concentrated. Okay, that point in space in which we can consider all the mass to be concentrated. In other words, this object and an equal massed object that is just a point mass would behave the same. Okay, what you see on the screen is a series of objects. Okay, sometimes individual objects, sometimes collections of objects, and it's often useful to try to find the center of mass of each of these. Okay. Often the center of mass is easy to find. If you take a look at our first example here, okay, which is the uniform sphere, okay, the sphere of uniform density, we often assume the Earth to be a sphere of uniform density, even though in reality the Earth is a little fat on the bottom, right? The South Pole is a little bigger than the North Pole, and it's not of uniform density on the inside. There's all kinds of crazy stuff going on. But that often is a very useful simplifying assumption. In the case of an object of uniform shape and density, the center of mass will be found at the geometric center. Right? The center of mass will be found at the geometric center. That's the case for objects of uniform density. Okay, if you go to the example underneath, right? This is two objects. Okay, but we can use the same guideline. We can first of all consider the center of mass of each rod and simplify it to a point mass, right? And now we've reduced this problem of two rods to a problem of two point masses, okay? And the center of mass of these two will probably be closer to this end, right? It's going to favor the heavier one. And you see other examples on the screen. We can consider some of these later, but there are tricks for determining the center of mass, and there's also a mathematical approach that we're going to take. So let's take a look at some of those. Before we do, I do want to consider one other term you might come across, which is called the center of gravity. Center of mass and center of gravity are often used interchangeably, and for the sake of this course, we can use them interchangeably. You see down there I've written that the center of gravity and the center of mass are considered to be, are going to be at the same point, except when you find yourself in a non-constant gravity field, which basically for us will be never. Okay, so you can consider the terms interchangeably. I will stick with the term center and mass. And you can see here a really cool example, right, of this acrobat. That's what acrobats are doing. They're constantly manipulating the center of mass to make awe-inspiring positions like this. Pretty darn cool. All right, moving on. There's an experimental way to find the center of mass of an object. Okay. And the way you can do that is it involves hanging the object from a pivot and letting it pivot. Okay, a real simple way to find the center of mass, like if we're looking at the center of mass in this system here, right, is just to find where it balances. Right, balance it on your finger, and you're going to find the balance point to be somewhere around here. Okay, and you know that the center mass then is going to run. Right, the center mass is going to run right through that line. Okay. If the object's irregular, okay, like you see over here, it's a little tougher to see where it is. I think we can see that there's more mass to the left, right? So if this is the geometric center, then probably the center mass is going to be more on this side, okay, because of all this mass here, right? So you can sort of eyeball it, but there's actually a way you can do this experimentally, and I'm going to show you that right now with an object that I have at hand. Okay, let's experimentally determine the center of mass of an irregularly shaped object. So, here's my irregularly shaped object. Okay, this is a bracket that we use in a physics experiment. And you can see by the shape, okay, that more of the mass is concentrated on this end, right? So if we look at it from a horizontal perspective, right, that's going to move the center of mass toward the heavy end, right? It's going to be more over here than in the center. But the other thing is to look at the center of mass right from the Y perspective, okay? And you might see that because a lot of the mass is down here, right? That might bring our actual center of mass outside the object somewhere in this region right here. So if we just had to guess, we would guess maybe right now that the center of mass is somewhere in this region right here. Okay? So here's how you experimentally determine exactly where it is. You take the object and you suspend it from two different points. Okay, I'm going to suspend it from the first point now, okay, from the top here. Okay, I'm going to let it hang freely. And then what I want to see is, I kind of want to make a line. So I'm going to use this string as a reference point. Okay, and the string represents the vertical from the pivot point. Okay, so what I want to do right now is I'm going to stop the video and I'm going to tape this string down so we can have it as a permanent reference point. Okay, and I'll come back after I've done that. Okay, it's a little bit hard to see. You can see it's right here. Okay, so now what I'm going to do is I'm going to pivot it from a different point. Right, I'm suspend it from a different point. Okay, and I know that orange is not showing up very well. And now what I do is I drop another vertical line, okay, which will be a second string here, and I see where those two intersect, like that. So you can see, and I'm bringing it up close here, you can see that the point of intersection, right, is right there, right, which means that our center of mass is, it's roughly where we said, right, it's definitely closer to the heavy end, right, and it's just barely outside the center of mass, okay. About right there. That's how you experimentally determine the center mass of an irregularly shaped object. Okay, so you just saw how to determine the center of mass of an object experimentally. Let's see how we might do it mathematically. Let's take a look at an example. Okay, we have two uniform spheres here. Okay, so we can mark the geometric centers, right? These are uniform spheres, so we know that their center masses are right there. Right, so we're basically considering where's the center mass of this two-point mass system. Okay. Now, there's some things that we can assume or figure out pretty easily, and that is that the center mass will be on the line that connects the two centers. Right. So let's see here. It's going to be running along this line right there. Right. Let me make that a dotted line. So we know that the center mass is going to be somewhere along that line there, okay, like that. And we just need to figure out exactly where it is. Now, when we say where, we're always talking about where with respect to what, and at what is our origin. So we need to determine an origin. Okay, we'll do that now. Why don't we just make the origin be one of the masses, right? We can make our origin be right here. That can be our origin. Right there. Okay, so that will be 0. Basically what we have to do is we have to consider the contribution of each object's mass to the total, right? What fraction it is of the total, and then how far is it away from a certain point. Okay, and so what we end up coming up with is the following. All right, your center of mass equation in one dimension looks like this. Okay, so here's the contribution of the first mass. Right, its mass times its position. Let me clean that up a little bit. Okay, times its position plus the contribution of the second mass by its position. Okay, or if I write this a little bit differently, right, if I divide both sides through by mass, right, you can kind of see it. It's kind of like an average, right? We're taking each one's contribution to the total, right, as a fraction of the total. But there's two ways you can contribute. You can have a lot of mass, right? You can have a lot of position. So let's work it out for this problem. Let's just make up a number here. Okay, let's say these are 2 meters apart. All right. So the center of mass position then would be, and we already know it's on the line between the two, right? That dotted line, that green dotted line. So mass 1 is 8 kilograms. But if we make this the origin here, like we said, right? It's located at the origin, so it actually will be times 0. And then 2 kilograms times 2 meters away, right, is that smaller one, and then we divide that by the total, which is 10 kilograms. And so we see then that this comes out to be 4/10, right? And the kilograms cancel, and it works out to be 4 meters. Okay. So what we find is that just as we assumed, which is that it's not at the geometric center, right? It's going to be to the left of that. Okay, like about right there. It's going to favor the heavier one. You just found the center of mass for this two-object system. We can expand this to more objects. Okay, imagine that you had a series of objects along a line here, right? Instead of two, you had like 4 or 5. So we could write this more generally in the following way. Okay, we could say M, dotted line, and we could just sum it up for all the objects, right? So for however many I have, right? We're not constrained to just this formula doesn't just work for 2 objects. And as you might expect, this doesn't just work in 1 dimension. Okay, I can write this in the 3-dimensional form, which would be like this: R being a vector, okay, from some point in 3-dimensional space. This is the equation that we'll use for all 3 dimensions. Okay, now practically speaking, what we'll do is we'll work in each dimension separately. But what I'm saying is that, hey, look, this works for all 3 dimensions, not just 1, even though our first example happened to be in 1 dimension. All right, let's take a look at another example. We'll come back to our rods here, like so. Okay, we talked about already what you can do is you can take an object of uniform shape, right, and find its geometric center. That'll be its center of mass. And what we can do in this problem here, right, is we can reduce this problem, okay, to this problem, which is much simpler, right? This center of mass 1 and center of mass 2, where we consider all the mass of each of the rods to be concentrated at those 2 points. And now we're just looking for that line that's along there, okay? That's supposed to be a straight line. Now you can see that's a diagonal line, okay? And that even when we reduce this problem to 2 points, we might have the issue of 2 dimensions, okay? Which is exactly right. What you'll do here, okay, is you can still use the same center of mass formula. You can see I've written them here on the right, but you're going to work in each dimension separately. So you're going to find the x-coordinate of the center of mass, and then you're going to find the y-coordinate of the center of mass, and then you'll take those 2 answers right, and those will become your coordinates of your final answer. So you can work separately in each dimension. All right, let's take a look at one more shape today that you saw at the beginning of the video. Okay, and that's this one here. Okay, and what I want to do actually, so this is some irregular shape, but I think what you realize is that we can break this into 2 regular shapes. So we're going to take a similar approach to what we did with the rods, even though I didn't solve that problem, sort of just walk through it. So what we can do is the following, okay, and it might be good to make kind of a conceptual guess where we think the center of mass will be before we actually solve for it, and then check and see if our intuition is right. So what I'm going to show you is the following. Let's drag this over here, okay? Let's just look at these 2 shapes separately. I think you'll agree with me. We're going to assume here that these are like flat shapes, okay, essentially flat shapes, 2D shapes that are of uniform density, right? If they're of uniform density, do you remember where the centers of masses can be found? That's right, at the geometric center. Right, at the geometric center. So, we're going to reduce this problem, okay? So let me now drag this back here, like so, okay, and make it one shape. The effect of that square is to pull this center of mass of the rectangle that way a little bit, right? So that we're expecting our final answer for the center of mass to be somewhere, you know, maybe like that. Maybe even that's a little too much, because the square is a lot smaller than the rectangle. So what we need here is we need some numbers. Okay, so I'm going to pause. I'm going to write some numbers in, some coordinates, all right, some lengths, and then we'll come back. Okay, I've written. Remember what we're doing, first of all, essentially here is we are representing, we're going to treat these, first of all, as like 2 different shapes, right? And then we'll bring those 2 point masses together. So, the first thing we want to do is let's determine by inspection, right, just by looking at it, what the centers of mass are of the 2 points. Okay. So, for the, and I guess what we should draw in, maybe we should draw in a coordinate system. Okay, so we're going to assume the bottom left of the rectangle to be the origin, right there. Okay, we'll call that 0, 0. And so the rectangle is going to have a geometric center of, actually, you know what, let's, just so we don't have to deal with decimals, let's change this 5, let's change that to 4. All right, then we can just divide that by 2. So for the big rectangle, right, say a rectangle, its center of mass is going to be at 0.05, right, going to meters now, 0.05, comma 0.02, like that. And then the square is going to be 0.07, right, 0.07, comma, top of the rectangle plus 1, that's 0.05, right? Those are the coordinates of the centers of masses of the two individual shapes, right? So we've now changed that problem to one that looks like this, okay? All right, so now we want to resort to our center of mass equations that we learned. But before we do that, we need to consider some missing information, which is we know that these dots are not weighted equally, right? One is clearly more massive than the other. But we weren't given masses. Well, the cool thing is you actually don't need mass for this because you can just do a ratio of one to the other. And since they're both of the same uniform density, which I didn't state at the beginning, but you know they kind of look the same, so that's what we were getting at, is we can just represent their masses, one as a multiple of the other. So let's calculate the areas, okay, and then we'll do the ratio. So the area of the rectangle is 6 times 4 is 24, right? 24 square centimeters. And the square is 4 square centimeters, right? So one is 6 times the other, right? So if we call this M2, then this is 6M2. Okay, so we're going to use those, and you're going to see that they work out pretty well. So again, remember we work one dimension at a time. Okay, so we'll say M XCM equals M1. Let's write these out. Okay, and let's substitute it in. Okay, let's plug in. The total mass would be 7M2. And that's what we're after. And M1 is 6. And the x coordinate is 0.05 of the rectangle, right? Plus 0.07. Okay. So you solve that, okay, for XCM, and I'll write out the y one. Okay, it's going to look similar. And when we solve those, okay, we get the following: XCM equals YCM equals, and these will be our x and y coordinates of the center of mass. Notice, by the way, that each term in both equations has an M2, right? So those M2s end up canceling, right? And then you're just dealing with numbers. So it works out pretty niftily. All right, here's where we end up with it. We end up with 0.052 meters, okay, and 0.024 meters, right? And so you see, right, because remember the coordinates of the geometric center were 0.05, comma 0.02. So in fact we were correct, but it was shifted very little, right? All right, there's center and mass in action, round one.